web, web of wonder. The whole intent was with the understanding that systems thinkers have been endeavoring to sell systems thinking to the world for the last 70 years with rather abysmal results. Rather than overloading people with a lot of theory and concepts, the idea was to present an experience in this first segment, which is why I call it Web of Wonder, so that you walk through and you look at a number of things that as you work your way through them, hopefully there will be some aha moments where all of a sudden you find yourself not where you expected to be. And the idea was to actually start out doing that in the first model, the bird feeder dilemma model, starting out talking about this person who is having a pleasant morning because they're having breakfast, watching the birds outside, and that's actually creating a pleasant feeling in the morning, helping them deal with the stress and turmoil that starts their day. And after this has happened several times, they go ahead and decide that they want to implement a bird feeder. And that's the extent of the forethought that goes into this situation, in that, well, this creates a pleasant morning, so let me go ahead and install a bird feeder. And after they install the bird feeder, they find out that, well, yes, the bird feeder increases the number of birds at the feeder, which is what they wanted, which makes for a more pleasant morning. And it increases the attractiveness of the garden, which adds to their pleasant morning and attracts more birds to the feeder. And the pleasant morning additionally helps them deal with their frustration, which was detracting from their pleasant morning. And then they find out that they realize that, oh, well, I have to buy birdseed. And I never thought about how much birdseed costs. So having to buy birdseed on an ongoing basis adds to my frustration. And the birds at the feeder create spillage, which increases the need to buy birdseed, which adds to my frustration. And the bird feeder attracts squirrels, the relentless, endless eating machine, which chases the birds away and creates spillage and increases the need to buy birdseed because they eat the stuff. And the spillage attracts rodents, which increases my frustration because I have to figure out how to deal with them. And the spillage promotes unsightly growth around the bottom of the bird feeder that I have to figure out how to do something about, which increases my frustration. And the birds at the feeder are now pooping all over the porch, and I have to figure out how to get that all cleaned up. So I end up actually having to deal with all of this stuff that I never actually gave a thought to begin with. I just said, well, the birds at the bird feeder create a pleasant morning, and as such, I'm going to install a bird feeder. The idea is that we can, in fact, be better at the things that we undertake if we learn to look further into the future about the implications of our actions. At times I liken it to the way that people play chess. People play chess at all kinds of different levels. Some people know what a chess game is. Some people know the moves of the pieces. Some people play chess and they play the current position and what they can move, and some people look at, if I move this, my opponent's going to do this, and then I'll have to do this. And they do that for some few number of possibilities on the board, and some people play the possibilities all the way to an end game. It depends upon the extent of how much trouble you might get yourself into if you don't pay attention to the implications of your actions. If you're comfortable looking at a situation and saying, if I do this, it will do this, and willing to deal with whatever might happen as a result of that, well then have at it. Though most people would prefer to have a better sense of what they're getting themselves into before they actually do it. So in terms of looking at the relationships, it's possible to better understand the implications of actually doing something. This is, and while what was created here is a sort of a qualitative picture of a set of relationships, which helps us develop a level of understanding. There is a level of understanding which can only be developed by using something called a simulation model. So that in this particular example, called moose and wolves, that if I look at the relationship between moose, there are moose births which increase the moose population and deaths which decrease the moose population, and there's a value for the typical birth rate and death rate of the moose. And if I run this simulation for 100 years with that set of assumptions, it tells me that after 100 years I have about 1.3 billion moose, which is kind of not likely, at least not on this planet. Though if I look at the situation or the context in a broader sense, I realize that there are also a wolves population, and there are wolf births that increase the population, and there's a birth rate for that, and a death rate which decrease the population. So if I run a simulation about the wolf population, it gives me a sense that over time the wolf population will simply die out and there won't be any wolves left at all. Though if I continue to study the relationships and find out that there is a relationship between the two populations, so that the population of moose actually influences the wolf birth rate, and the wolf population influences the moose death rate. Taking those into consideration and developing a simulation, I get a behavior pattern that's completely unexpected simply from looking at the diagram itself, so that the two populations are intertwined and they rise and fall based upon the way that the populations interact. So that's sort of the intent for this segment, in that you begin to get a sense, that there are interactions that we can benefit from if we seek them out and study them, to give us a better sense of what the implications of those relationships are. And in terms of models, there's an analogy that I developed at one point in time, in that I think of a model the way I think of a play, in that a model is a story that unfolds based upon the relationships. And I can think about a play in the same way, in that a play is a series of acts, and within each act there are actors and relationships between the actors, and each act in the play is a part of a story that unfolds from beginning to end, so that we think about developing models in the same way that we think about the way that a play is put together, and the model is intended to tell a story over time. So there are some things here about learning, and then there's three essence properties, 1, 2, and 3. And these are intended to point out that I'll let you go through individually, but what it ends up pointing out, piece by piece, is that there are three simple structures, and these are the only structure. In other words, think of it as the basic pieces of a Lego construction set. You have three different kinds of pieces, and everything that you create, you end up creating from these three different types of pieces. So one of them is a feedback independent, or a flow that's independent of the value of the stock itself, so that stuff flows in and it accumulates. So what's in here grows over time, but the rate at which it grows is independent of what's there. And this is the graph for it, so that over time it's just a linear flow. Whatever this flow rate is the rate at which it grows. The second structure is a goal-seeking or a balancing structure, where there's some goal and some current state, and it's the difference between the two of those that defines what the state change or the flow is, based upon some factor between 0 and 1, just to deal with the extent of that change. So it is, over time, it's the difference between these two that defines what the flow is, and the flow is meant to move the current state in the direction of the goal, which is why it's called a goal-seeking structure. And if you look at this, you'll see that the typical pattern is that the current state moves in the direction of the goal because of the state change, the flow, and as the current state gets closer and closer to the goal, the state change gets smaller and smaller over time. And once the current state reaches the goal itself, there's no difference between the two of them, so there's no more state change, and all of the activity stops. This is the second type of structure that you run into. And the third structure is a reinforcing structure, where given some result, some activity produces a result, and that result influences more of the same activity that caused the result to begin with. It's a reinforcing structure that produces exponential growth. You might think about this the way as similar to the way that bacteria multiplies in a culture, or the way that savings increase in a savings account. Of course, I'd really like to find a savings account that increased like this. It's still an exponential growth, but it's a very small growth. So that you end up that there are three basic structures that, regardless of how complex or complicated the model is that you're looking at, it's actually fabricated or constructed out of three very simple structures that interact. And if you figure out the way to unfold this to someone as a meaningful story, it's not nearly as complex as hitting them with the whole thing at once. I mean, I tell people that the best way to eat an elephant is one bite at a time, as opposed to having it fall on you. So that this, and then there's three types of structures, and then I talk about, present three different types of models, which are done here, so that we talked about rich pictures, the idea that you can have relationships and depict those relationships with pictures to cause the model to just to convey more information or more easily convey the information that you're trying to get across. Or you can have a causal loop diagrams where there is more information contained in the diagram because you explicitly define the relationships between the components, and you can do that with or without pictures. The causal loop diagrams are causal loops because of the influences that exist and the nature of the relationships, which are depicted to be either reinforcing or additive or balancing, and they actually form loops, and you can tell the difference between the loops because if you walk the circle and there are 0 or an even number of balancing loops, it's a reinforcing structure, and if there is an odd number, then it's a balancing loop. And this is the same as the structure I showed a moment ago for exponential growth, and this is the same goal-seeking structure that I showed before, only this is the causal loop equivalent of the stock and flow diagram. And the stock and flow version, or the stock and flow type of model, is more explicit in terms of the structure because it identifies which things are stocks and how the stocks change using flows. And the only way that you can alter the value of a stock is because of an inflow or an outflow. And the definition of variables, which are used to influence each other or flows. And for every one of the relationships in the model, there are actually formulas that define how that relationship acts so that you can actually view the implications of that set of relations in the stock and flow diagram, which you can't do with the causal loop diagram. So depending upon what it is that you're trying to convey and the audience that you're trying to convey it to and the extent to which you're trying to understand something, you determine whether or not it's appropriate to develop rich pictures or causal loop diagrams or stock and flow simulation models. And in the future segments, we'll get into these in more detail, and you'll actually learn how to create them. At this particular point in the process, it's simply important to understand that there are different types of structures and how it is that they differ, and what it is that it's appropriate to use them for. And then as you progress, there's a set of guidelines that you would follow when you develop models, and this thing called the essence of and, which is my attempt to reduce the concept of systems thinking to a single word, and that word is and, so that what happens is for a particular situation, an approach to developing a model is for any given situation, I look at the elements and I ask myself, and what does this influence and what influences it? Knowing that what I'm looking for are loops because it's the feedback that has a greater influence over the way that something operates than anything else. So if I begin with this situation that I have some crop-eating insects that lead to crop damage, and I'm a farmer and the bugs are ruining my livelihood, I ask myself about, all right, the crop-eating insects leads to crop damage, and I know what that's doing to my livelihood, and what does the crop damage influence? Well, it influences me to apply pesticides because I know that the pesticides kill the crop-eating insects, so I have because there's one balancing influence, I have a balancing loop that's intended to control insects. The difficulty is that it seems that year after year I have to spray more and more to kill the crop-eating insects. So there must be something else that's going on here. So I ask myself, I look at the individual components and I ask myself, what do they influence or what influences them? And in terms of the crop-eating insects, well, I know it's obvious that they have births. I know it's because I don't kill all of them. They have births, and the births increase the number of crop-eating insects. Though this alone doesn't seem sufficient to deal with my dilemma in terms of there being more and more crop-eating insects year after year, and why I have to spray more to control them. So I continue to look at the pieces, and I say, oh, okay. There's a nasty aspect of insects in that by applying pesticides, I end up promoting pesticide immunity, which results in more crop-eating insects because I don't end up killing so many of them. So by applying pesticides and promoting immunity, which results in more crop-eating insects, which leads to crop damage, which encourages me to apply more pesticides, I have a pesticide immunity reinforcing structure that's taking me in exactly the wrong direction of what it is that I'm trying to go in. So is there something else that's going on in the structure? If before I planted these crops, there wasn't a crop-eating insect problem before, so why was that? Well, as it turns out, there used to be a controlling insects that devoured the crop-eating insects. Though by applying pesticides, I end up killing most of the controlling insects so that they no longer devour the crop-eating insects, which leads to more crop damage, which encourages me to spray more. So I end up with a predator destruction reinforcing loop, which is also taking me in a direction that I absolutely don't want to be going in. So I'm being my own worst enemy because I'm continuing to do things that are actually making the problem worse as opposed to making the problem better. I would probably be better off if I actually stopped applying so many pesticides and figured out how to promote the development of controlling insects to devour the crop-eating insects so that I wouldn't have the crop damage. Though, were I to do that, I should also then think farther ahead and say, what is it that the controlling insects are going to want to eat once they eat all the crop-eating insects? Because they're probably still going to be hungry. And if I don't do something else, how long can I continue to apply pesticides before I ruin my water supply, or ruin the fields so that I can't grow crops, or ruin my own water supply so I have to truck in water to feed my animals, or. So it's in terms of developing the set of relationships, you simply have to continue to keep asking, what does this influence and what influences this, to build a better picture of the relevant relationships to better understand what's going on so that you can get out of the mode of being your own worst enemy. And so this is the essence of AND. It's, as I said, an attempt to distill systems thinking into a single word, and that word being AND. So that's pretty much what the whole sequence is about. And then when you get to the Web of Wonder, there's a summary of all this, rich pictures, and then there's an assignment to go ahead and post your thoughts about this to the discussion thread for this particular week, to share your thoughts with the rest of the group and have me comment on your thoughts, and then begin for the next week. So that's the way that the Web of Wonder unfolds and the reason for it. And I see that there are still no questions. So I guess maybe we're going to end a bit early. If you have questions, please post them to the most appropriate discussion thread, and I will answer them. Please don't start a new discussion unless it's something you really want to go to everyone that's participating in the program, because everyone will get a copy of it. When you get a copy of a new discussion that started, you don't automatically follow that discussion. Presently, you have to actually go to that discussion in Kumu and either post something to the discussion or click on the button in the upper right and say that you want to follow the discussion. So if that's it, I guess we will end it there, and I will see you in the next session. Take care, all. Bye.